So hello dear students, welcome to Gate Wallah. We are going to start the lesson on LTI system and its properties in the one short series. Today we are going to cover LTI systems, convolution and properties of convolution. Okay, so these three are very important with respect to GATE exam. Okay, and many a times questions has been asked based on convolution, based on LTI system properties. Okay. In this chapter, we will not be covering the complete convolution. That is, we will not be solving the convolution of two signals completely. Rather, we will be focusing on the questions which are asked in GATE exam based on convolution. And what is the pattern of the question? The pattern of the question is the impulse response of the system is given, okay, and the input is given, and we have to find out the value of the output at a particular time instant, okay. So these are the type of questions that we'll be dealing with in this whole class. Okay. So first of all, let us start with the representation of any signal in terms of delta function. Suppose we have any signal. Suppose we have any signal xn. Okay, any random signal xn. Any random signal xn, and this is the zero location, let us say. This is the zero location, let us say. Now, we'll write this signal xn in terms of delta n, okay. Now, what is delta n? We know that delta n is a signal which is 0 everywhere and it is 1 only at 0 location. Then it is 0 again. And then it is 0 again, okay. It is at n equal to 0, it is 1, and then it is 0 again, and also here. So, what is delta n minus 1? The delta n minus 1 is 0 everywhere, only at n equal to 1, 0 location is here. At n equal to 1, it is 1, okay, and so on. Similarly, delta n minus 2, similarly delta n minus 3 will be at n equal to 3, delta n minus 2 will be at n equal to 2, and so on. So this will be the deltas and the shifted deltas, okay. Now, if we try to write it, if we try to write the signal xn, we can write the signal xn as like this. This is value is 3 at location minus 2, at location minus 2. So we can write it like this. Value is 3 and location is given by del n plus 2. So value is 3 and location is minus 2. The value is 2 and location is minus 1. So location is minus 1. Similarly, we can see that the value is 2 here and location is 0, and location 0 is given by del n. Similarly, at n equal to 1, it is minus 1. Okay, value is minus 1, but location is so value is minus 1 and location is 1. Okay. Similarly, here 2, value is 2, location is 2, and so on. And so on. So here we can see that, here we can see a very important result, that is this del is showing the location and the multiplication factor is showing the value at that particular location. Okay. So we can write it like this also. If we write 3 as x2, x minus 2, sorry, x minus 2 del n plus 2, value and location x minus 1 del n plus 1 value and location x0 del n and so on. Okay, so are you able to understand this? How we are able to write this? Yes, I hope all of you are able to understand this, how we are writing it, because we are simply putting the value of the signal and the location, value, location, value, location, value, location. Okay, so delta is telling the location and the multiplication factor is telling the value. So for simplified version, we'll write it like this. X minus 2 is the value of the signal at n equal to minus 2, and this is showing the location. X minus 1 is the value at minus 1 location, and this is showing the location. Okay, now thus we can write it like this. We can write xn in terms of del n, that is xm del n minus m, m going from minus infinity to infinity. So this is the way we write any signal in terms of deltas. This is the way we write any signal in terms of deltas. Okay, so this is a very important representation, very important expression. Okay, now exactly in the similar manner, so since we have write any signal xn in terms of deltas, it is like this: xm delta n minus m, where m is going from minus infinity to infinity. Okay, here the summation variable is m. Summation variable is m. Now exactly in the similar manner, we can write xt also in time domain. Obviously the summation will convert into integration. Okay, here we have the summation variable, here we'll put the integration variable tau. Okay, here we have the variable of the output, here we'll put the variable of the output del t and minus the integration variable d tau. Okay, so this is the way by which we write or represent any signal. We represent any signal xt or xn in terms of deltas. This representation is very important because we will be using these representation in our analysis today. Okay, these two representations are very important. So you have to remember this representation. Okay, so xn is equal to summation minus infinity to infinity xm del n minus m, xt is equals to minus infinity to infinity x tau del t minus tau d tau. So these are the two representations which are very important, and we will be using these representations in our today's class. So now let's move on to the LTI systems, response of the LTI systems and the properties of the LTI system. In the last class, in the last series, we studied what is linear and time invariant systems. Okay, so linear and time invariant, we know what is it. So now let us say that if the input to the system is delta t, if this is the input to the system, if we put delta t as input to the system, then we'll get the response. Obviously, if we give some input, we'll get some response. So we'll get the response, and that response is called the impulse response. Okay, so when impulse is given as the input to the system, this is the LTI system. Okay, this is the LTI system. We get the impulse response, and impulse response is represented by HT. Simply we can say that delta t is the input, HT is the output. Delta t is the input and HT is the response. Okay, impulse response. Okay, now if we shift the input, we shift the delta then obviously the response will also get shifted by the same time. So let us say we shift the delta input by tau. So response will also get shifted by tau. What property we have used here? We have used the property that the system is time invariant. The system is time invariant. So we got h of t minus tau. Now we multiply the input by some constant x tau. We multiply the input by some constant x tau. So using linearity property, we can see that the result will also get multiplied by the same time constant by which the input is getting multiplied. So we can see that del t minus tau response is ht minus tau, and xt multiplied by del t minus tau, we are multiplying the input with a constant x tau. So result will also get multiplied by the same constant x tau using the linearity property or homogeneity property. Okay. Next, now we integrate the input. We integrate the input x tau del minus tau d tau. We integrate the input. We integrate the input term. Now integration is a linear operation, so the same operation will be done on the response. So minus infinity to infinity. Okay, so this will be the result. Now this expression, have you seen this expression somewhere? Yes, we have seen this expression in the earlier slide. This is xt only. This is xt only. So finally, what is the result that we got? The final result that we got is this. That is minus infinity to infinity x tau del t minus tau d tau. The response of this signal, the response of this input is minus infinity to infinity ठीक है ना, ये मिल गया. So we can see that this is input, this is xt only, this is xt only. So we can say that when xt is applied as the input, the response that we get from the system is minus infinity to infinity okay. So minus infinity to infinity x tau h of t minus tau d tau. Okay, so this is the final result that is very important, that is very important. And let me write this response very clearly. So if ht is the impulse response, ht is the impulse response of the LTI system, okay, ht is the impulse response of the LTI system, and xt is any input. Xt is any input to the system, then response of the system is the response of the system is given by minus infinity to infinity x tau h of t minus tau d tau, and this expression is called the convolution, that is xt convolve ht. This is convolution, okay, this is convolution. And always remember the expression of convolution, that is xt convolve ht. This is the symbol of convolution. This star symbol is equal to minus infinity to infinity x tau h of t minus tau d tau. We can see that here the variable of integration is tau. Here the variable of integration is tau. Okay. So these are the things that you should remember. Okay. If ht is the impulse response, xt is the input to the system, then the response of the system is xt convolve ht, and the expression mathematically is minus infinity to infinity x tau h of t minus tau d tau. Okay. So suppose we have any system, any LTI system. Suppose we have any LTI system with impulse response ht, and the input is xt, then the response is xt convolve ht. Okay, xt convolve xt. Okay. Now what is the type of questions that are asked in the exam? Now just one more thing here, one more very important thing here is that always remember that xt convolve ht is equal to minus infinity to infinity. Remember this formula. Okay, this is very important formula. Here the variable of integration is tau. Integration variable is tau. We can interchange them also. Interchange them means this is also equal to x of t minus tau h tau d tau. Okay, h tau d tau. So we can interchange this also. We can interchange the terms also. So there is no issue. That is we can use any of the two formulas. Okay, whichever is convenient to us. Now what is the type of questions that are asked in GATE exam? Okay, generally we face the problems, that is we are very afraid of convolution of two signals, but actually in GATE exam the complete convolution of two signals is done only by Laplace transform or Z transform in case of discrete. Here we will only be dealing with the pattern of the question, that we have to find out the response at a particular time instant only. Okay, we have to find out the response at a particular time only. So how to solve these type of questions? Let me tell you with the help of example. First of all, let's see the steps, then we'll do the examples for clarity. Okay, now so LTI system is given to us. LTI system is given, and LTI system is always given with the impulse response. We have its impulse response. We have its impulse response. So LTI system is always given with its impulse response. Without impulse response, LTI system is of no meaning. Okay. Now we have to find, we have xt as input to the system. Input xt is also given to us. We have to find the output at a particular time instant. we have to find out the output at a particular time instant. So let us say we have to find out the output at t equal to 5, any value t. It can be 3, it can be 2, it can be 5, it can be 10, it can be of any value. Okay, so let us find out the output at t equal to 5. So from this formula, this convolution formula, okay, we know that yt is equals to xt convolve ht. We know that the output yt is equals to xt convolve ht. So we have to find out y5. Y5 will be equal to minus infinity to x tau. Now coming back to this slide again. So this is your yt. Okay, this is your yt. Now if we want the output at t equal to 5, if we put t equal to 5 here, then this whole expression, only here we will put 5. Okay, we'll put small t is equal to 5. So when we put t equal to 5 here, we'll put t equal to 5 here. So what will be y5 equal to? Y5 will be equal to minus infinity to infinity x tau h of 5 minus tau d tau. Okay, so what is the method? The method is simply find out x tau, simply find out h at 5 minus tau, multiply them and integrate the result from minus infinity to infinity. You will get y5. Okay, so this is the example. First of all, let me write the steps. So what are the steps? Step number 1 is find x tau. That is already given in the question, right? Second, find h of 5 minus tau. Third, multiply x tau with h of 5 minus tau. We'll multiply these two and then integrate minus infinity to infinity, integrate these, the product, multiply these two and then we integrate the result from minus infinity to infinity. This will give us y5. Okay, in place of 5 we can have 3, we can have 2, we can have any value. So these are the steps. Let us take one example on this. Let us take one example. So xt is given to us, that is ut. Impulse response is also ut. We have to find out the output value at n equal to 4. Okay. So simply and directly coming to the question now, input is ut, impulse response is also ut. We have to find out the output at n equal to 4. So y4 is equal to minus infinity to infinity x tau of 4 minus tau d tau. Okay. So what is x tau? xt is ut. So x tau will be u tau. Simple. U tau. Now h of 4 minus tau, ht is equals to ut. h of 4 minus tau will be u of 4 minus tau. U of 4 minus tau d tau. Okay. Now we have to first of all find out u tau and u of 4 minus tau. Then we have to multiply them and then integrate the result to get y4. So what is u tau? U tau is very simple. U tau is like this. U tau is like this. This is u tau. Now what is u of 4 minus tau? U of 4 minus tau will be equal to 1. We know the definition of ut, right? U of 4 minus tau will be equal to 1. where 4 minus tau is positive, or we can say it is tau less than 4. Or we can say that it is tau less than 4. Great. And it is 0 elsewhere. 0 for tau greater than 4. So what is this? We can easily draw it. It will be something like this. 1.0, and this is u of 4 minus tau. Now we multiply these two. We multiply these two, and when we multiply these two, we will get only a rectangle. We will get only a rectangle from 0 to 4. Height 1. What is the area? What is the area? So first of all, we found x tau. This is your x tau. Then we got h of 4 minus tau. Then we multiply these two. This signal is from 0 to infinity. This is from minus infinity to 4. When we multiply these two, both are having value 1 and 1. We'll get a rectangle from 0 to 4, height 1. Now we have to integrate this signal from minus infinity to infinity to get y4. Integrating this from minus infinity to infinity means the area of this rectangle. So we can see that y4 is equal to area of the rectangle, that is 4 only. That is 4 only. So I hope everyone is able to understand this concept. This is a very simple concept, and only we'll be dealing with this concept in convolutions. Okay, we'll not be completely solving the convolution of two signals because that will be done by the Laplace transform. Here we are worried about the questions or the format of the questions where we have to find out the output at a particular time instant only. Okay, now we have to find out yt at t equal to 15. Okay, so very simple question. Xt is given to us, height 2, it's a rectangle from 0 to 10. Okay, and input ht, the impulse response of the system is given as ut. We have to find out the output at t equal to 15. Okay, so very simple question, let us solve it. So y15 is equal to minus infinity to infinity x tau h of 15 minus tau d tau. So first of all, x tau is same, that is it will remain the same, that is a rectangle from 0 to 10, height 2. We have to find out h of 15 minus tau. So h of 15 minus tau is equal to 15 minus tau is equals to u of 15 minus tau. And u of 15 minus tau, the same expression of ut, that is it will be equal to 1, where this is positive. 15 minus tau is positive when tau is less than 50. 0 elsewhere. So this will be a signal that is from minus infinity to 15, it will be like this. So it will be 50, height is 1.0. Great. Now x tau will remain the same. X tau will remain the same, that is x tau will be the rectangle of height 2.0, 0 to 10. Height 2.0, 0 to 10. This is x tau. Now, when we multiply this rectangle with this u of 15 minus tau, this signal is from minus infinity to 15, height 1. This is from 0 to 10, height 2. When we multiply these two, we will get this rectangle only. Again, just see, we have a signal which is from minus infinity to 15, height 1. We have a signal 0 to 10 only, height 2. When we multiply these two, we will get only 0 to 10, height 2 only. Okay, height 2 only. So we will get This is the product 0 to 10. This is the product of x tau. Okay, now we have to then integrate this. We have to then integrate this. We have to find out the area of this rectangle. So area of this rectangle will be 20. Height is 2, width is 10. That is 20. So what is the value of the output at t equal to 15? That is 20. Okay, I hope all of you are able to do it. Very simple and beautiful question. Now this question, we have to find out the output at t equal to 3. We can see that xt is equals to 20 height from 5 to 10 and from minus 10 to minus 5. Okay, then ht is equals to height 2 and that is from minus 7 to 7. Okay, minus 7 to 7. So we have to find out y3. For y3 we need minus infinity to infinity x tau h of minus tau d. Okay, so this is simply a rectangle, right? So we can see that h tau is simply a rectangle. H tau is simply a rectangle which has height 2 and the range of tau is minus 7 to 7. 0 elsewhere. So what will be h of t minus tau? The h of 3 minus tau will be 2 height from the range of 3 minus tau will be from minus 7 to 7. Okay. Now we subtract 3 from both sides, minus 10 to 4. So this will give us minus 4 to 10 and 0 elsewhere. Is this correct? I hope all of you are able to do it. First of all, we subtract 3, so we will get minus 10 and 4. Then minus tau will invert the sign. Minus 4 to 10 will be the range. So we got this also. Got this rectangle. Minus 4 to 10. Height is 2.0. This is h of minus tau. H of 3 minus tau. This is what the result is. H of 3 minus tau. Now xt is from minus 10 to minus 4 and 5 to 10. 5 to 10. So if we multiply this with x tau, so let me draw x tau here itself. So x tau is from 5 to 10. Okay, and from minus 5 to minus 10. This is from minus 10 to minus 5 and from 5 to 10. What is the height of x tau? The height of x tau is 20. Height is 20. Now, when we multiply these two, we can see that these two are very separate apart. Here it is non-zero, but here x this signal is 0, so product will be 0. Here it is non-zero from 5 to 10. This is also non-zero, and the value is 2. Value is 20. So when you multiply these two, we'll get the value 20. When you multiply these two signals, we will get a single signal. We'll get a single signal or single rectangle from 5 to 10, height 40. Why height is 40? Because the height of this rectangle is 20, height of this rectangle is 2. When you multiply these two, we'll get 40. Okay, and the width will be from 5 to 10 only, because here this is 0, this is non-zero. So obviously the product will be 0. So we'll get the product will be 5 to 10, height 40, and the value of the output at t equal to 3 will be the area of this signal, this product, and this will be equal to 40 into 5, that is 200. I hope all of you are able to do it. 200 is the correct answer, the value of the output at t equal to 3. Great. All of you are able to do it? Great. So, this type of questions, I think all of you will be able to do it. Now, let's see one more signal. The impulse response ht is given to us, that is 4 rect of t by 10. And input xt is a constant, that is 10, that is 5. Input is a constant 5. Input is a constant 5. ht is 4 rect t by 10. Now we have to find out the output at t equal to 10. A very simple question. Let us solve it. Okay. So we know that yt is equals to minus infinity to infinity x tau h of t minus tau d tau. Okay. So we have to find out the output at t equal to 10. Y10 is minus infinity to infinity. X tau is a signal which is a constant. Okay, it is a constant signal 5. So this is a 5, this is 5. So we can keep it outside. 5 h of 10 minus tau theta. So this will come out 5 minus infinity to infinity h of 10 minus tau theta. Now we have to, like, we know that ht is a rectangular signal. ht is a rectangular signal. And what is this ht? We can easily draw it. It is a rectangle which has height 4 from minus 5 to 5. Height is 4 from minus 5 to 5. Height is 4.0. This is your h tau. ht or h tau doesn't matter. Okay. Now just think. If we shift the signal or invert it and we integrate this rectangle from minus infinity to infinity, repeating the point again. If we shift this signal, invert this signal and we integrate it from minus infinity to infinity, the answer will always be, or we can say that the area of the rectangle will not change. Repeating the point again. If we have this rectangle, we invert this, we shift it, area of this rectangle will not change. The area will always be equal to height 4, width 10, that is 40. So this value will always be 40. Even if we invert the signal, we shift the rectangle and we integrate it from minus infinity to infinity, the area of the rectangle will not change. So this is 5 into 40, that is 200. Okay, so this is the answer. I hope this point is clear to all of you. Great. Okay. Now let's move on to this question. This is a very beautiful question, and the same concept, the concept of this question was asked in electrical gate exam. Okay, so let's do it. So now let's solve this question. We have the input, that is 5 cos 2 pi upon 20t. We have the LTI system, which is the rectangular, having the impulse response a rectangular one, right? So we have to find out the output at t equal to 0. So xt is a periodic signal. This is a periodic signal cos has period 20. This is periodic period 20. Okay, periodic with period 20. This is rectangular pulse which is from minus 10 to 10. This is a rectangular pulse that is from minus 10 to 10. Minus 10 to 10, height is 5. So this is your ht. Now this is your input. So we have to find out the output at t equal to 0. So y0 is equals to minus infinity to infinity x tau h of minus tau d tau. Okay, so we can see that h of minus tau means the reversal of this, it will be same like this only. Okay, ht is like this, h of minus tau will also be same like this. Okay, just time reversal will remain the same. So this will be, if we multiply these two, we'll get minus 10 to 10, minus 10 to 10, 5 times of x tau d tau, this is y0. Now we know that x tau is a cost signal which has period 20, and if you see the integration range, this is also 20. So we are actually integrating cost signal over a period, and integrating a cost over a period is always a 0. Repeating the point, this range of integration is 20, and the input xt is cost signal which has period 20. So we are integrating a cost signal over its period. So integrating a cost over its period will also give us, or will always give us, a 0 result. Okay, so the answer is 0. Okay, we are integrating cost over its period only, over its one period. Okay, so the output is 0. Now we have to find out, we'll move on to the convolution of signal with a delta function, right? So xt convolution ht is equal to minus infinity to infinity xt h of t minus tau d tau. Okay, we know this formula. Okay, xt convolution ht is equals to minus infinity to infinity x tau h of t minus tau d tau. Now if in place of ht we put delta t, so xt convolution delta t will be equal to minus infinity to infinity x tau h of, sorry, in place of this we delta t minus tau d tau. Okay, so we can see that this is simply, we have seen this expression somewhere. Yes, we have seen this expression in the starting of the class. This is xt only. So we can see that xt convolution delta t is equal to xt. xt convolution delta t is equal to xt only. Okay, great. Always remember this. Now before moving to this, let us first of all finish the properties of the convolution. Okay, 2 or 3 properties are there, then we'll move on back to the convolution with the delta, and then we'll come back to the properties. Okay, so convolution is a commutative operation. Commutative operation means xt convolution ht is equal to ht convolution xt. That is, we have seen this, that is minus infinity to infinity x tau h of t minus tau d tau is equal to minus infinity to infinity x of t minus tau h tau d tau. Okay, so these two are equal to, means we can interchange the inner terms, we can interchange the brackets, then also the result will be same. Okay, so it is commutative. Just remember this, that this is a commutative operation. Okay, this is a commutative operation. Now let's move on to the time shifting property. Time shifting property says that if xt convolution ht is equal to yt, now if we shift one signal, then the result will also get shifted by the same time. If we shift one signal, the result will get shifted by the same time. If we shift another signal, this one, then the result will also get shifted by the same time. If we shift both the signal, then the result will get shifted by like this. Okay, so this is the time shifting property, this is the time shifting property, and we can get the result like this. Okay, so before moving to width property, let's come back to the delta convolution with a delta. Okay, convolution with a delta. So we know that xt convolution delta t is equals to xt. Xt convolution delta t is xt itself. So xt convolution del 4t will be equal to, now del 4t is equal to convolution del at plus b. Let me just tell you the result. Okay. This del at plus b. You remember del at plus b can be written as, del at plus b can be written as 1 upon mod a del t plus b by a. Okay, this can be written like this. Now as we know that xt convolve delta t is equals to xt. Okay, now in place of t, if we put t plus b by a in this and apply the time shifting property, if we replace t by t plus b by a in this signal, then obviously the result will also get shifted. Okay, so using the time shifting property, this will be 1 upon mod a of t plus b by a. This will be the result. So I hope all of you are able to understand this. Sir, how you are getting this? Let me explain you one more time. We know that xt convolve delta t is equal to xt. Xt convolve delta t is equals to xt. If we do the shifting in this term, for example t plus 4, then the result will also become t plus 4. If we do the shifting in this term, we'll get shifting in the result, time shifting property. If we put t plus b by a, the result will also be x of plus b by a, the time shifting property. So I think all of you are able to understand this. Great. So now let's come back to the question. So this can be written as xt convolve 1 upon 4 delta t. So xt convolve delta t is equals to xt itself. So the result will be 1 upon 4 xt. That is xt by 4. So I think B is the correct answer. I think all of you are able to do it. Great. Xt convolve delta t is xt itself. Now xt convolve del 2t. So this is again xt convolution 1 upon 2 delta t. So this will be xt upon 2. B is the correct answer here. Now xt convolve del t minus 4. Now since we know that xt convolve delta t is equal to xt, and if we do the shifting in delta term, then the result will also get shifted. Okay, so this will be xt minus 4. Okay, great. So this is how the time shifting property can be used in the convolution with delta questions. Okay, so we have already seen that the convolution integral is commutative. We have seen the time shifting property. Now let's see the width property of the convolution. So width property is very important and it is used for convolution of two rectangles. So we'll be seeing the convolution of two rectangles in the later slides. First of all, let's see the width property. The width property says that if yt is equals to xt convolve ht, if yt is convolution of two signals, then if xt is non-zero, xt is non-zero only for time only for time range TXL, TXH, okay, only for time range TXL to TXH, and if HT is non-zero, only for range THL to HH, means we have the lower limit of times and the upper limit of time. So lower limit for XT is TXL, upper limit is TXH, lower limit for HT is THL, upper limit is THH. Then XT convolution HT will be non-zero. Will be non-zero for time range will be non-zero for time range. What will be the time range? Add the lower limits and add the upper limits. So add the lower limits TXL plus THL so add the lower limits, add the upper limit. So this is the range of YT where YT will be non-zero. Okay, so let's take an example. Before moving to the distributive property, let's move on to the convolution of two rectangles. Okay, because this width property is very important and it can be used here. So we can see an example also. We can see the convolution of two rectangles. So there are two cases here. Here we have two cases. First case is two rectangles of equal width, two rectangle of equal width. Second, two rectangle of different width. Two rectangle of different width. So first of all, let's see the two rectangles of equal width case. Two rectangle of equal width case, let us see. Two rectangle of equal width. Okay. So let us say we have two rectangles and they have equal width but height are different. So let us say it can be anywhere, the rectangles can be anywhere. There is no boundation that they have to be at the origin. They can be anywhere. They can be anywhere. Okay. So let us say the width is W. Both are having width W. Both are having width W. One is having height H1. Another is having height H2. Another is having height H2. So the convolution is always a triangle. Convolution gives a triangle. Convolution gives a triangle. Now, it is very important that can we find out the starting limit and the end limit of the result? Yes, by the width property, we can get the starting and the end time instant of the result. Okay, so always remember when the width are equal, the result will be a triangle. First point. Second point, we can get the limits on the time axis of the triangle. Okay, how? By using the width property. By using the width property. So we can get the result. The result is always a triangle, as we know. Now the only thing that is left is we have to find out the height of the triangle. We can find out the starting point. Yes, the starting point and end point we can get. Great. So how we can get the starting point and end point? So this is the starting point of, मान लीजिए X signal है, starting point of this signal, starting point of this signal. So if we add the two starting points, we will get the starting point of the triangle. If we add the two end points, we will get the end location of the triangle. Okay, end location of the triangle. Now, it will be maxima at the center. It will be maxima at the center, and what will be the maxima value? The maxima value will be equal to height h1 multiplied by height h2 into width. Okay, height of the rectangle 1, height of the rectangle 2, and width. So we have to multiply h1, h2 and w. So this is the result. Okay, so let's see an example. Suppose we have two rectangles. One rectangle is from -10 to -4. The width is 6. Okay, and the other one is 4 to, let us say, 10, or we can keep it anywhere, 10 to, let us say, 16. Okay, the width is 6, width is 6. Height, let us say height is 10, here height is 5. So we have to convolve these two. We have to convolve these two rectangles. These two rectangles are of equal width. You can see width is 6 directly. Now we will get our triangle. We will get a triangle from, we can get the initial location, we can get the starting location. Starting location is adding the starting location of the two rectangles, -10 plus 10, that is 0. The starting location is 0. What is the end location? Add the end values. So -4 and 16. So the end value is 12. So this is the time range. Obviously maxima at the center, that is 6. Now what is the maximum value? Maximum value is height of 1, that is 10. Height of 2, that is 5, multiplied by width. 10 into 5 into width, that is 300. So this is the triangle. So we can get the convolution of two equal rectangles, equal width rectangles anywhere very easily. We can get this we can get this convolution very easily. Okay, so this is case 1, that is convolution of two rectangles of equal width. Now when the width is not equal, when the width is not equal, so suppose we have two rectangles, then we get a trapezium. Okay, then we get a trapezium. Suppose we have two rectangles of different width. They are of different width. They don't have the same width. Okay, so this is having width W1. This is having width W2. They are not equal, obviously, but one is having bigger width, one is having smaller width. Okay, we have two signals. They have different width, but obviously one will be having a smaller width, one is having a bigger width. Now we get a trapezium. Convolution gave us a trapezium. Okay, we get a trapezium like this. Okay, now let us just see this. We can find out the starting point and end point, right? We can find out the starting point and we can find out the end point. There is no issue in it. Now we have to find out the marking of this. We can find out the starting point and end point. Starting point and end point we can find very easily. So this location will be away from the starting point. This is the starting point. We can get the starting point using width property. This point where it is changing will be away from the starting point by how much duration? That duration is equal to the width of the smaller rectangle. That is W2, width of the smaller rectangle. Similarly, this mark will be away from the end point by width of the smaller rectangle W2. And then we have to find out the height of the trapezium. Height of the trapezium is equal to H1 H2 into width of the smaller rectangle. H1 H2 multiplied by width of the smaller rectangle. Okay, so smaller rectangle is very important. We can find out the start point and end point. We can find out this point by moving from the starting point by W2 distance and moving from the end point by W2 distance. We can get these points. Then height of the trapezium equals to H1 into H2 into W2. Okay, great. So let's see an example. Let's see an example. Suppose we have two rectangles. One rectangle is this, the other rectangle. One rectangle is from -5 to 5. Other rectangle is 2 to 4. Okay, height is 10, height is 2. Okay, great. Okay, so we can see that the width of the smaller rectangle is 2. Okay, so now we will get a trapezium. Obviously, they are not of equal width. So we will get a trapezium from what is the range? -5 and 2 will be -3. Okay, 5 and 4 will be 9. We will get a trapezium. Okay, now what will be this mark? This mark will be away from the start point by how much distance, how much time? That is equal to width of the smaller angle, that is by 2, duration that is -1. Similarly, this will be 7. What will be the height of the trapezium? Height of the trapezium will be H1 into H2 multiplied by width of the smaller rectangle, that is 20 into 10 into, that is 400. So height of the trapezium is this. So we can get the height, we can get the starting point, end point, and these mark points, the center ones. Okay, very easily. I hope all of you are able to do it. Great. Okay, so this is how we can convolve the two rectangles very easily. Now let's coming back to the properties. We have seen the width property and we have used it also. Okay, now distributive property. This is a very simple property. XT convolve HT plus CT. This can be written as, we can distribute it okay, we can distribute it. Next, differentiation property. So differentiation property can be used many a times. It's a very simple property. So if XT convolve HT is equal to YT, then if we differentiate XT, we will differentiate the YT also. If we differentiate one signal, the result will also get differentiated. Similarly, this is also Y dash T. Next, if we differentiate both the signals, then the result will get differentiated 2 times. Okay, so this is how the differentiation property works. Okay, So this can be used if in any question it is asked. Okay, great. So now let's move on to the area property. Area property says that what is the area of a signal? What is the area of a signal? So area of a signal is equal to minus infinity to infinity the signal xt or ht or anything. This is the area of the signal. Okay. So if the area property says that if yt is equal to convolve ht, then area of y is equal to area of xt multiplied by area of ht. Remember this. So a question can be asked that find out the area of yt, that is xt convolve ht. Always remember that the area of yt is equal to area of xt multiplied by area of ht. Okay, great. So we have seen the convolution of two rectangles. We have seen the both the cases, width equal and width not equal. Okay, so many times question has been asked in this format also, that this equation is given to us. Obviously it looks like similar to the convolution, but let's solve it. So we have to find out the impulse response of the system. Impulse response of the system means we have to simply replace the input term by del t. So we have to apply, we have to find the impulse response. So how can we find the impulse response? We simply replace the input by delta. We simply replace the input by delta. This is your yt. Now this is delta t minus tau. That is delta tau minus 2. Delta tau minus 2. So what is the location of delta? Location of delta is tau equal to 2. Location of delta is tau equal to 2. Now we are integrating from minus infinity to t. Okay. Here the variable is tau. Here the variable is tau. So let me draw a axis for you. Suppose this is tau axis and the location of delta is tau equal to 2. This is the location of delta, this delta. Okay. Now, since we are integrating from minus infinity to any variable t, we are integrating from minus infinity to variable t. There can be two cases. T is less than 2 and t is greater than 2. Since we are integrating from minus infinity to t and t is a variable, so there can be two cases. If t is less than 2, obviously we can see that if t is less than 2, then delta is outside the integration limit and the answer will be 0. And if t is greater than 2, if t, this variable t is greater than 2, then delta is within the integration limits. Delta is within the integration limits. And then just to recall you, whenever the delta is within the integration limits, so whenever the delta, let me recall you this concept. So what was the concept? Let us say delta is within the integration limit. Suppose this is the integration x alpha del alpha minus 2 d alpha. So here the variable is alpha. So if the delta is within the integration limit, we simply put the answer of this integration is we simply put alpha equal to 2 in this expression, right? You all remember that? We simply put alpha equal to 2 in this expression. Same case here also. Here the variable is tau, integration variable is tau. When the delta is within the integration limit, we simply put tau equal to 2 in this expression. We simply put tau equal to 2 in this expression. So for t greater than 2, delta is in the integration limit delta is in the integration limit, and we simply put tau equal to 2 in this expression. So the impulse response will be equal to this. So we can see that the impulse response will be equal to e to power minus t minus. Okay, so this is the result that we get. Okay, so we have, what is the final result? Finally, we have this, that is impulse response is equal to 0 if t is less than 2, t is greater than. So you got the result, and you got the method also how to solve these questions. Very simple, you simply replace x by delta, and then the normal integration of delta that we have seen in chapter 1, that is tau equal to 2 is in the limit, then the answer is non-zero. We simply put tau equal to 2 in this equation. If t is less than 2, then delta is not in the integration limit and the answer is 0. I hope this is clear to all of you. Similar question here. We have to find out the impulse response of the system. We simply replace x by delta here, minus infinity to t minus 7. This is your ht, impulse response. Now we can see that the delta is located at t equal to 3. Delta is located at t equal to 3. Okay. Now we are integrating from here. We can see that the location of delta is at tau equal to 3. We are integrating from minus t to t minus 7. Okay, minus infinity to t minus 7. Simply we can see that the integration limit will contain tau equal to 3 only when t minus 7 is greater than equal to 3. That is, t is greater than equal to. So integration limit will contain the delta only when t is greater than equal to 10. So here we have two results. Here we have the result, that is ht will be equal to the impulse response will be equal to 0 if t is less than 10, because if t is less than 10, the delta will not be in the integration limit. But if t is greater than equal to 10, then integration limit will have the delta, and then the result will be simply equal to, by replacing tau by 3 in this equation, e to power minus 3 is the answer. Okay, so simply you have to see that delta is within the limit or not. If it is in the limit, then the answer is non-zero. Simply replace tau by the value or the location of delta in the function. So simply replace tau by 3 here, we'll get the result. Otherwise, if t is less than 10, the delta is not in the integration limit and the answer is 0. So I hope all of you are able to do it. Great. Now let's move on to the discrete LTI systems. Exactly similar analysis that we have done earlier for the continuous time LTI systems, the same will be doing here. The same analysis we will be doing here. What is the analysis? First of all, we know that we can write any signal xn in terms of delta. Okay, this is the way we can easily write. Xn equals to minus infinity to infinity xm del n minus m. We have seen this expression in the starting of the class. Okay, now the same analysis that we have done in the continuous time LTI system, that is, first of all we give the input del n. The response that we get is impulse response Hn. This is called impulse response. This is called the impulse response. Now if we shift the input, then obviously since the system is time invariant, we'll get h of n minus m as the output. So del of n minus m is the input, h of n minus m is the output, time invariant system. Now if we multiply the input by a constant xm, then due to homogeneity, the result will also get multiplied by xm. Okay. Now finally, if we do summation, the summation is a linear operation. So due to linearity, we do summation x of m, h of n minus m. Sorry. Here we have x of m delta n minus m going from minus infinity to infinity. Okay. And the result will also be equal to, we'll apply summation on the result, minus infinity to infinity. Okay. So this is the result. So we can see that the result is, this input. So if we see this input, we know that this is xn, right? So if we give xn as the input to the system, then the response is xm h of n minus m, minus infinity to infinity. This is your response, that is equal to yn. And this expression is called convolution in discrete domain. And thus you can say that yn is equal to xn convolve hn. Yn is equal to xn convolve hn. And what is the expression of convolution? This is the expression of convolution. Great. This is the expression of convolution. Okay. So what is convolution in discrete domain? The convolution is this only. Yn is equal to xn convolve hn. Then the result is m equal to minus infinity to infinity xm h of n minus. Okay. We can interchange the terms also. There is no issue in it. We can interchange the terms. Okay. Then also the result will be same. So this is the discrete convolution. Okay. This is the discrete convolution. We can solve the questions very easily in this case. So again, the same format of questions are asked in GATE exam. That is, the impulse response is given, the input is given, and we have to find out the output at a particular time instant only. We have to find out the output at a particular time instant only. Okay. So what is the method? The method is same as we have done in the continuous time case. Okay. The method is same as we have done in the continuous time case. So now let's see how to solve these type of questions. Okay. So here input xn is given and the impulse response of the system is also given to us. So input and the impulse response both are given to us. So yn we have to find out at any particular interval of time. For example, at n equal to 5 we have to find out yn, that is the output of the system. Input xn and Hn are given. Input Xn and Hn are given to us. So we have to find out Yn at n equal to 5. So using the formula, we can see that y5 is equal to summation xm h of 5 minus m minus infinity to infinity. This is the whole method. Okay, we have xm. We need to get h of 5 minus n by shifting or inversion, and then we multiply the two and add all the terms to get y5. Okay, we get xm, then we get h of 5 minus m, we multiply them, then we add all the samples of the product. Okay, so we have this example, we have one example. We have to find out y2, we have to find out the value of the output at t equal to or at n equal to 2. We have to find y2. Okay, so we have to find y2. What is y2? y2 is x of m h of 2 minus m summation minus infinity to infinity. Now we have xm, that is this is your signal xm. Okay, and we simply need to get h of 2 minus m. We need to get h of 2 minus m. So we know that Hn is equal to 1. Hn is equal to 1 from 0 to 4. Okay, amplitude is 1 only. It is 1 from n equals to 0 to 4, or we can say that 0 to 4 and 0 elsewhere. Okay, so from here we can get h of 2 minus m will be equal to 1. 2 minus m is less than equal to 4. 0 to 4. So we can find out the range of m where this signal is non-zero. Okay, we subtract 2, we get minus 2 to 2 and 0 elsewhere. Okay, and 0 elsewhere. So minus 2 to 2, we have h of 2 minus m. Now we have xm, we have h of 2 minus m. Now we multiply these two signals. We will multiply x of m multiplied by h of 2 minus m. Now since this signal h of 2 minus m is 1 from minus 2 to 2, okay, from minus 2 to 2. So when we multiply it with this xm, it will get multiplied only at 0, 1 and 2. For negative values, this xm is 0, and for rest of the values hm is 0. So when we multiply, we will get a signal that is present only at 0, 1 and 2. What is the value at 0? At 0 it is 1, 2 and 3. Okay, so it is, this is 1, this is 2. Okay, now this is the product. Now we add all the samples of this product. So y2 is simply adding all the samples, that is 3 plus 2 plus 1, that is 6. Okay, great. So this is the answer. The answer is y2 is equal to 6. So this is the way we can easily solve to get the answers. Generally in GATE exam or in competitive exam, continuous time questions are asked. Okay? The discrete time questions are not asked in the exams. Here we have to find out y of minus 2. Here we have to find out y of minus 2. So first of all, we will have to calculate again the equation, and then we have to calculate the signals, and then we multiply the signals to get the result. So let us find out. Y of minus 2 is equal to summation xm n equal to minus infinity to infinity. First of all, we know that h of n is equal to, h of n is a signal which is from minus 2 to 5, minus 2 to 5. And 0 elsewhere. So we can see that h of minus 2 minus m will be 1 for the range minus 2 minus m minus 2 to 5. Now we add 2 all in all the terms, so we'll get minus 7 to 0. I hope all of you are able to get this. So this is h of minus 2 minus m is 1 from minus 7 to 0. We add 2, we will get 0 and 7, and then we invert the limits and 0 elsewhere. So we have this h of minus 2 minus m from minus 7 to 0. Now when we multiply this 2, that is we multiply hm and we multiply, now we multiply xm with this signal. Minus 2 minus m, then since h of minus 2 minus m is non-zero for minus 7 to 0, so it will get multiplied with xm at minus 3, minus 2, minus 1 and 0 at these 4 values only. And since the height is 3, not 0, sorry, the height is 3.0. The height is 3.0, here height is 1. Okay, height is 3.0, sorry. Height is not 1, it's 3. So now when we multiply h of minus 2 minus m with this x of m, we will get that this 2 will get multiplied only at these 4 terms, 0, minus 1, minus 2, minus 3, okay. So we will get a signal which is equal to okay. So we'll multiply these with 3, okay. These terms will get multiplied by 3. So here 1 into 3 is 3, the height will be 3. Here also height will be 3. At minus 2, this signal has value 2, but this signal has value 3. So the multiplication will be 6. Similarly, x has value 3, h has value 3, so this is 9. So summation of all the values, summation of all the elements of this signal will give us a result y of minus 2. That is equals to 9 plus 6 plus 3 plus 3. That is 21. Great. So this is the answer. I hope all of you are able to understand this. We simply have to multiply xm with this signal, not this signal actually, with this signal. And since this signal is from minus 7 to 0 only, so this will get multiplied with xm for the negative values 0, 1, minus 1, minus 2, minus 3. So since this signal has value 3, so 3 will get multiplied by 1, 3 will get multiplied by 1, 3 with 2, 3 with 2, 3 with 3, sorry. So 9, 6, 3 and 3 will be the samples of this multiplication result, and we all add the samples to get the value, that is 21 is the correct answer. Great. Now convolution of any discrete signal with the impulse. So a very simple result, let us find out. We know that xn convolve hn is equal to xm h of n minus m minus infinity to infinity, okay. Now if in place of hn we put del n, okay, we put del n. So what is the result? We know that this result is equal to xn itself. So it is same as that of the continuous time domain. Okay, so xn convolve del n is equal to xn, okay. So before moving to these results, we will first of all see the properties of the discrete convolution. Okay, properties of the discrete convolution. The properties are almost similar. Okay, first is commutative property, that is 𝐿𝑁 convolve 𝐻𝑁 is equal to 𝐿𝑁 convolve 𝐻𝑁. Okay, 𝐿𝑁 convolve 𝐻𝑁 is equals to 𝐻𝑁 convolve 𝑥𝑁. It is commutative in nature. Time shifting property. Time shifting properties are exactly same as that of the continuous time domain. 𝐿𝑁 convolve 𝐻𝑁 is equal to 𝑌𝑁. Then if we shift this by some time, that is n0, then result will also get shifted by the same time duration n0. Okay. Then result will also get shifted by the time shifted in the signal. Okay, the same result as that we have done in the continuous time, the result is same. So if we do the shifting in both the signals, then result will get shifted by both the times, that is m0 and n0. So the result or the property is exactly same as that of the continuous time case. Okay, now let's come on to this delta convolution. Now first of all, before moving to the delta convolution, we need to recall some delta properties. Okay, what are the properties? Now delta an is equal to delta n, because in discrete we only have the value equal to 1 where the term is 0. Okay, so delta an is equals to delta n, that's very clear. Similarly, delta an plus b is equal to delta n plus b by a or 0. Either it is this or it is 0. So it is equal to this when b by a is integer. Otherwise, if b by a is not integer, this is a 0 signal. I hope you all remember these properties. So if you remember these properties, then everything is very much clear and very easy. So del 4n is equal to del n itself. Okay. In case of continuous time, it is 1 by 4 delta t, but here it is del n only. So this is same as 𝑥𝑁 convolve del n. The answer is 𝑥𝑁 itself. Okay, I hope you remember this property. Next, 𝑥𝑁 convolve del n minus 1. Now this is time shifting property. 𝑥𝑁 convolve del n is equal to 𝑥𝑁. Now if we do the time shifting, then it is 𝑥𝑁 minus 1. It is 𝑥𝑁 minus 1, so this is the result. Okay, A is the result. Great, time shifting property. Now this. Here we can see that this delta, del 4n minus 9, del 4n minus 9 can be written as del n minus 9 by 4. Now since this location is not an integer location, so this delta is 0 everywhere. This is a 0 signal. So this is a 0 signal. So 𝑥𝑁 convolve 0 is 0. Okay, 𝑥𝑁 convolve 0 is 0. This is a 0 signal because this is not an integer. Same in the this also. This delta can be written as del n minus 7 by 5. So here we can see that this delta is a 0 signal because this is not an integer value. 7 by 5 is not an integer. So this is a 0 signal. Convolution result is 0. Great. So like this you can easily solve the questions. Now let's move on to the width property of the convolution. This is also exactly same as that of the continuous time domain case. What is the property? The property is if yn is equal to xn convolve hn, xn is non-zero for the time range, that is the lower limit to upper limit, okay. hn is non-zero for the time range from the lower limit to the upper limit, then yn will be non-zero for the time range. Do you remember the property in the continuous time? Yes, I think you all know it. So yn will be non-zero for the time range, addition of the lower limits, till addition of the upper limits. Addition of lower limits plus addition of the upper limits. So this will be the range of yn. Okay. There is one more property in this discrete case, but I will tell you later on in the later slides, where I will be telling you one more method that is called tabular method of convolution of the discrete signals. Okay. Distributed property, this is very simple property, that is xn convolve hn plus cn is equal to xn convolve hn plus xn convolve cn. Okay, this is the property. Great. Next, after difference property is there, differentiation property is not in the discrete case. Okay, it is in the continuous case. This property is not there in the discrete case. Now, sum property. Exactly similar the way we have the area property in the continuous time, we have sum property in the discrete time. This property is very beautiful property. Suppose yn is equals to xn convolve hn and summation yn n equal to minus infinity to infinity. This is s of y. S of y is equal to summation of all the samples of yn. Similarly, s of x and s of h, sum of all the samples of x. Sum of all the samples of h. Okay, so sum of all the samples of x and h. Then the sum property says that sy is equal to sh multiplied by x sx. This is exactly same as that of the area property in the continuous time. Okay. Now, there is one more method for discrete convolution. There is one more method of discrete convolution. What is the method? This is a very beautiful method. Okay, suppose we have two signals, any random discrete signal 1, 2, 3. This is the zero location. Okay, hn is 2, 0, 1. This is the zero location. Now we want to convolve them. When we want to convolve them, so we can see that both are starting at zero location only. Both are starting at zero location. So the result will also start from the zero location. So the convolution can be done by the formula also. We know the formula of convolution, but there is one more method that is called the tabular method, matrix method, or any method you can call it. So what is the method? What is the method to find out yn? Yn is convolution of these two signals. So what is the method? Step number 1 is just write xn by reversing it. Just write xn by reversing it. So reversing it means the signal is 1, 2, 3. Reverse it. Place it in the reverse order. So 1, 2, 3. Reverse hn also. So 2, 0, 1. Reverse it. 2, 0, 1. Now In class 5th and 6th, we do multiplication of numbers. Simply multiply these two numbers. Simply multiply 321 with 102. What is the steps? Sir, you multiply 2 with 1. Yes. 2 with 2. Yes. 2 with 3. 6. You put across. 0 with 1. 0. 0 with 2. 0. 0 with 3. 0. We put double cross. We multiply this 1. 1, 2 and 3. Great. Now we add the terms. Now if we, here the point is, whenever we add, and if in case there is a carry, do not put carry to the next digit. Put the number directly here itself. This is the only thing that is different from the multiplication. No carry has to be given to the next place. Okay. So here the result is 2, 4, 7, 2, 3. This is yn, but this yn is just placed in opposite order, in the reverse order. So just reverse it again to get yn. So this is 32742, reverse it, and yn is equal to 2, 4, 7, 2, 3. And since both the signals are starting at 0 location, the yn will also be start at the 0 location. Okay, yn will also start at the 0 location. So I hope all of you are able to do it. Great. This is the method. Reverse xn, reverse hn, multiply them and add to get the yn. But yn, this will be in the reverse order. Just put it away, put it in the reverse order to get yn. Okay. And since both the signals are starting at 0, the yn will also be start at 0. One more example. 1231 219. Okay. So again we reverse it. 1231 and 219. Multiply them. So 212, 224, 236, 212. Cross. 111, 122, 3 and 1. You put a double cross. 919, 9218, 9327, 919. Great. We add them. So here we have 2, here we have 5, 9, 2, 11, 11, 6, 17. So then no carry has to be given in the next place. 17, 18, 19, 20, 23, 28 and 9. So just reverse it to get yn. So it is 2, 5, 17, 23, 28 and 9. So this is the starting location. Okay, so this is the result of convolution. I hope all of you are able to understand this. Okay. Now one more method, one more point here is, suppose the same question but xn is equal to 1, 2, 3, 1 and 0 location is here. hn is equal to 219. So here the result will not change. Okay, the steps will not change. Irrespective of the 0 location, you have to follow the steps. Steps are the same. Just reverse it, reverse this, multiply and add. You will get yn. Okay, so we'll get yn. The values will not change. The values will not change. The values will remain the same. 2, 5, 17, 23, 28, 9. 5. Okay, the result will not change. Okay. Now, we just have to see where the arrow has to be placed here. Okay. So here we can see that this is the 0 location. This is -1, -2. So xn is starting from -2. xn is starting from -2. This is -2 location. Great. hn, this is 0 location. This is -1. So hn is starting at -1. So from the width property, we can see that yn should start from -3. So the values will remain the same. Only the first value will be at -3, -2, -1, 0. So this is the 0 location. Again, I'll repeat the point. Zero location does not affect the values of the result. Convolution values will remain the same. So the result is same. Don't worry about it. Okay. This is zero location. So this is -2. This is zero location. This is -1. So if we use the width property, the starting point will be -3 in yn. So this is -3, -2, -1, 0. So this is the zero location. So like this, you can get the answer. You can easily solve this also. There is no issues in it. Great. Now let's move on to the interconnection of the systems, interconnection of two systems. There are two methods in which we can connect the systems, LTI systems. That is a series connection, cascade connection, or parallel connection. Okay, series connection, that is also called cascade connection, or the parallel connection. Okay, so now let's see what is happening. Suppose we have a system. We have two systems which are connected in cascade. Okay, now xn is given as input. This is first LTI system which has impulse response h1n. Second LTI system which has impulse response h2n. This is xn convolve h1n. Okay, we can see that xn is given as input. This is the LTI system h1n. We convolve it and we get the result xn convolve h1n. Okay, this is again as input to the system. So the output, final output will be this xn convolve h1n convolve with h2n, the simple property of the LTI system. So we get xn convolve h1n convolve h2n. Okay, so if we replace this series connection by a single system, if we replace this series connection by a single system, which has impulse response, h1n convolve h2n. Okay, if we replace this series combination by a single system that has impulse response h1n convolve h2n, then this whole setup is same, because if input is xn, then the output will be xn convolve the impulse response of the system. And what is the impulse response? h1n convolve h2n. Okay, simple thing. Okay, simple. So what is the conclusion? The concluding statement here will be, the concluding statement will be, the concluding statement will be the conclusion statement will be, if we have two or more systems in cascade, two or more LTI systems in cascade, or series connection, then it is equivalent to single system with impulse response equal to convolution of impulse response of systems in cascade. Okay, so conclusion is, if we have two or more LTI systems in cascade, then it can be replaced by, or it is equivalent to a single system with impulse response equals to convolution of the impulse response of the system in cascade. Okay, Great. Now the next point, if we have two systems in parallel like this, if it is in parallel. So if the input is xn, this xn will go here. This system with h1n impulse response. This is x2n. Input is xn. This system is having impulse response h2n. So here we get xn convolve h1n. Here we get xn convolve h2n. Now here we are adding or subtracting it. Sorry, here we are adding or subtracting it. So final result will be, the final result at this point will be xn convolve h1n plus minus xn convolve h2n. So this can be written as okay. So xn convolve h1n plus minus h2n. So we can say that we can replace this whole combination. We can replace this whole combination. So we can replace this whole combination by a single system. By a single LTI system with impulse response equal to h1n plus minus h2n. Okay. So we have impulse response equal to h1n plus minus h2n. Okay. So just remember that in case of series connection or cascade connection, we convolve the impulse responses. In parallel connection, we either add them or subtract them, as we can see here. Is this clear to all of you? I hope all of you are able to understand these points very easily. Great. Now let's move on to the last part of the chapter. The last part of the chapter, that is impulse response is given to us. We know the impulse response. Okay, we know the impulse response of the LTI system. From the impulse response, we have to find out. From the impulse response, we have to find out that the system is causal, non-causal. That the system is causal, non-causal, stable. Okay, so we have to find out the stability of the system, causality of the system. This is the type of problem that is asked. Okay, so we know that the LTI system, the impulse response defines its all the properties. Okay, so for LTI system, impulse response is very important. So here we will understand how to find out all the other properties of the LTI systems using the impulse response. So using the impulse response, we have to find out the causality. We have to find out the causality. We have to find out the stability. Mainly these two things are very important. So let's come on to check whether the system is causal or not. So there are 2-3 statements, just remember them and you can solve the questions very easily. If HT is 0 for t less than 0, if the impulse response is 0 for t less than 0, system is causal system. System is causal system. Okay. If HT is 0 for t greater than 0, then it is anti-causal system. Then it is called anti-causal system. Okay. If it is not satisfying these two properties, if none of above the satisfied, if none of the above satisfied, then it is non-causal system. Then it is non-causal system. So I hope all of you are able to get this. HT is 0 for t less than 0, causal. HT is 0 for t greater than 0, anti-causal. If none of the above satisfied, then it is non-causal system. So I hope all of you are able to get this. Great. Similarly, for the discrete case, Here only I'll write. For the discrete case, for discrete systems, the analysis is almost same or the statements is almost same, but there is one critical point here, right? So Hn is 0 for n less than 0. This will be causal condition. This will be for the causal condition. Hn is 0 for n greater than equal to 0. Remember this. This is very important. Here equality is very important. Hn is 0 for n greater than equal to 0, then it is anti-causal. If none of these is satisfied, then it is non-causal. Then it is non-causal, okay? So remember that in case of anti-causal here, it has to be 0 for n greater than equal to 0. Equality sign is very important in case of discrete. Continuous may, there is no equality sign, there is no issues about it, okay? Now, for memoryless and memory system. So you remember memoryless systems are called static systems and memory systems are called dynamic system. Great. So to check whether the system is memoryless or static, the statements are very easy and very simple. If the system is memory system, if the system is memoryless system, always remember that HT has to be of the format of K times delta T. Hn has to be of the format K times delta N. So, if the impulse response is K times delta T or K times delta N, then it is memoryless system. So this is very easy. If it is K times delta T or K times delta N, it is memoryless. Otherwise, any other signal, if impulse response is any other signal, then it is otherwise system is memory system. System is memory system. Okay, so for static, it is very important that it is of this format. Okay, otherwise it is dynamic. Okay, so I hope you remember this. Great. Stability of the LTI systems. So for stability, I'll give you one statement and everything will be very much clear. For stability, HT should be absolutely integrable. For stability, for a stable LTI system, HT should be absolutely integrable, means minus infinity to infinity mod of HT dt should be less than infinity. Okay, it should be absolutely integrable. That is, impulse response should be absolutely integrable. Now, here the point is, we can say if the impulse response is energy signal, then the system is stable. This is a jugaad. If impulse response is energy signal, then it is a stable system. Okay, then it is a stable system. Also, one more point here. Similarly, for Hn, if Hn is absolutely summable, then it is a stable system. If it is absolutely summable, then it is a stable system. Then it is a stable system, otherwise it is not. So here also absolutely summable means mod of Hn minus infinity to infinity, this should be less than infinity. So these are the properties of the systems. So for causality, you need to check for Ht has to be 0 for t less than 0. For anti-causal, it has to be 0 for t greater than 0. Okay. For memoryless, it has to be k delta t only. For stability, it should be energy signal or it should be absolutely integrable signal. Okay. Absolutely integrable signal. So these are all the properties of the LTI systems. Okay. So I think all these properties are very much clear to all of you. So thank you, dear students. Bye bye. Take care.